Cool. Okay, go there, and the Brisbane.net user group is there. Definitely, someone was asking me earlier, what's the best way to stay up to date with some of the new technology and things coming out? The user groups are awesome, and really appreciate the people that actually run them, because they're also they put a lot of effort into making them happen. So we talked about part one, covered a bunch of patterns here as part of the part one of the talk. I kind of think of the first three as kind of crawl, and then we kind of got to the walk phase. Part two, we're going to start running, and we'll go kind of pretty deep on a number of dimensions, and cover a couple different topics that kind of build on top of the patterns that we covered in the first part of the talk. And so if you missed the first part of the talk, we covered how to set up your environment with automated source control, scripts, and continuous integration so that you have a nice, fast, repeatable workflow. So as you make changes, you can get them out quick and react fast. The next couple were just sort of basic web development best practices for scaling out across your infrastructure and taking advantage of autoscale, which is a nice built-in feature of Azure. One thing I didn't mention as part of autoscale that I should actually mention is with Azure, you now pay by the minute, not the hour. So as you're automatically scaling out and down the number of servers that you have, the beauty is you're only paying for the actual minutes that they're running. So if you burst for 20 minutes and then burst back down to reduce your VMs, you're only paying for that 20 minutes of compute, which is a nice differentiator and saves you lots of money. We talked about enterprise single sign-on, and I talked about how you can actually do single sign-on with Azure Active Directory and integrate your corporate on-premise environment. Someone asked a question about, can you also do single sign-on with Office 365? The answer is yes. And then someone during the break asked a question about, hey, wouldn't it be great if you could do everything I'm showing here with SharePoint? One of the cool things about the new version of SharePoint and the new SharePoint app model is it's built on top of Azure. And so everything I'm showing here in this talk today, going forward, you will be able to do with SharePoint apps. In fact, you deploy them, you can use autoscale, you can do everything I'm showing here with SharePoint as well. And part of the glue that ties that together, again, is Azure Active Directory. And we're working very closely with the Office 365 team in terms of enabling that. I then talked about different data storage patterns you can do with Azure, and then also talked about data partitioning strategies, and in particular, horizontal and vertical partitioning as a way to kind of design your data model so you can scale up as you get more data. And I talked about the 3 V's of variety, velocity, and volume as you want to think about in terms of what data strategy you're going to use. So for part 2 now, we're going to start running a little bit more. And we're going to kick it off by talking about something called unstructured blob storage, which is a really cool data storage option that we have inside Azure. And if you remember, we said we have a couple of what we call platform as a service capabilities and then infrastructure as a service. On the platform side, we talked about relational, and we use that with SQL databases in some of our demos. I talked about table storage, which is a key value NoSQL store that we have as an option. We're going to see that a little bit later on when we talk about logging. Blob storage then is the next one we're going to look at, though, in depth. And it basically gives you a way to do unstructured files inside Azure. And it's managed, again, as a platform as a service component, which means it's a service you can use. You pay only for what you use. And it lets you store literally up to petabytes of storage. Some of our biggest customers store literally hundreds of petabytes on top of blob storage. And it's a really powerful system that lets you build some great solutions. So we're going to use that inside our Fix-It solution. So what does blob storage give you? Think of it as a highly scalable, durable, available file system in the cloud. It uses a REST API, so it exposes a REST API to program against it. We have .NET, Java, Ruby, other language wrappers that you can use on top of that REST API. And basically, it lets you store files in the storage system. You can keep them completely private. You can also, if you want to, go ahead and publish them over HTTP. You can do it either in an unsecured way, so you can say, hey, anyone can download this image or this file. We also have a really nice model we call kind of SaaS keys, which basically lets you give a short-term lease to a client so that they can access that file over HTTP. And after a certain point in time, it'll expire, and then you can choose to let them re-authenticate or not. But it provides a way that you can now store lots and lots of files in the cloud and restrict access to specific clients that you want to give access to and be able to do it for different time periods as well. And basically, in general, anytime you're building a cloud app in Azure and you basically want to store a lot of content, a lot of stuff, whether it's images, videos, music, uploaded spreadsheets or PDFs or what have you, you're going to want to think about blob storage as a potential mechanism that you can use. It can really help, and it's really easy to set up and take advantage of. In fact, to set up, it's basically all you need to do in order to get started with blob storage is you basically literally just go new data services storage account, and you can name it, you choose where in the world you want to run it, and 15, 30 seconds later, you got a storage account you can now start putting content within. One cool feature I should mention about storage that you can kind of see here is this thing called enabled geo-replication. And what that basically enables you to do is every time you pick a location where you want to run this, say for example, I want to run this in my storage account in the East US, or I could pick different parts of Asia. Once we open up our 2 regions inside Australia, we'll have one in the Victoria region and one in New South Wales. Basically, they're 500 miles apart. And so you can pick your primary region where you want to store your content in. If you click this enable geo-replication, then every time you write your file to, say, the Victoria data center, we will, in the background, automatically copy the content also to the New South Wales data center as well. And what that means is if Godzilla comes out of the ocean and stomps on the data center, your data is safe somewhere else. It's a great way, even if it's not Godzilla, if you think about fires, earthquakes, hurricanes, tsunamis, whatever natural disaster, floods that you need to worry about, it's basically a way that you can actually replicate your data somewhere else and know that you can have a failover scenario in the event of emergency. And so it's a really nice differentiator. If you don't want that feature, just untick it and it won't happen. We also make sure that we only replicate the data within a geopolitical boundary. So our 2 regions inside Australia, they will geo-replicate between themselves, but they don't geo-replicate outside of Australia. Same way the US data centers don't replicate to Europe and vice versa. And that way you don't have to worry about your data ever leaving the sovereignty. So you create a storage account. Once you do that, and by the way, that script that I showed earlier in part 1, this is how I could create the storage account in PowerShell, so you can, again, completely automate it. Once you have a storage account then, you can start programming against it. And you can do a couple different things. And what I'm doing inside this application is every time the app starts up, I basically check to see whether or not I connect to the storage account, which is the first 2 lines. And then what I do is I basically, in the first red circle, I basically connect to it and say, is there an images folder within it? If there's not an images folder, then I go ahead and programmatically create it. That's the container.create if not exists. And then if that succeeds, what I do is I go ahead and I actually set the permissions so that the images folder has public read access, so that anyone can go ahead and download images from within this images container. And that's basically all the code I need to add to my application so that when it starts up, it makes sure it has access to the storage account and that there's an images folder with read-only access that it can store things in. What I then have is code within an upload photo method that I use within this application. Every time someone goes ahead and uploads a fix-it request and uploads a photo. So if you remember, going back to our application here, when I go ahead and create a new fix-it, I could say, clean my room, please. It's messy. Assign it to someone. Pick an image. And when I do that upload, and I hit create, I'm uploading that image through HTTP. And then what this code is doing right here is a little helper function we're going to integrate into our application. It takes the image, it's called by the ASP.NBC app. And what this thing basically is doing, that first line in red, is it's going ahead and creating a dynamic URL that I can then save this image to. And so I'm basically just adding tasked photo with a couple random parameters. I stick in a GUID, and I figure out what file extension of the photo was. I then basically can write these next 3 lines of code, which uploads the image to my blob storage account and saves it within the images container. And so basically you can see I just set the content type, I hit upload from stream, and I'm uploading the streamed photo from my web server. I basically get back the full path to that blob, and I basically then just embed it inside my HTML, and now a browser can go ahead and access that directly. And you'll notice if I go here, oops, let me create another one, blah, assign it to myself, upload this, and look at the details. You'll notice that image is there. If I look at this actual image in the HTML, you'll see something like this, which is that image is being stored in skyguwest.blob.core.windows.net images, and that's that task photo with a GUID that I just created. That's where that image is actually being stored. And basically that code that I just showed you is literally all the code necessary in order to take the image, construct that URL, upload it, and then get back the URL, and then I basically just render it inside the system. So that's basically how easy it is in order to integrate blob storage. Right now, the blobstorage.net API is synchronous. An async version is coming out a little bit later this month, at which point that can also be fully async inside your web tier. So again, all these operations are not blocking anything inside your web server. So how am I then using this inside my app? So basically, what I basically did here is I have an iPhoto service interface, and I basically just have this upload photo that takes an HTTP posted file. This photo service class implements everything necessary to talk to my storage system. So that's that code to create the container that I showed in that first slide. And this is that upload method that has all the code in order to save the file, and it just returns the file path back. That's literally all the code that talks to the blob system in my entire application. And then what I basically do inside my app is just every time someone creates a new task, all I basically do is I create a fixed task, which we're going to persist in the relational database. I get back the photo URL by basically uploading the photo, and that code that you saw on the slide just returns the path, and then I just squirt this into the database. And so the only thing that's stored in the database, the image is not stored in the database. What is stored is the file path in the photo URL property, and then when I render it out, my browser just talks directly to Blob Store. Because the image's container is public, it can then go ahead and just render the image inside the page. So fairly simple way with only roughly 20 or 50 lines of code total throughout the entire system. But now I'm storing all my images outside the database. So my database schema, or my database size is going to get a lot smaller than it would if I stored the images inside it. And because I'm storing it in blob storage, I can now store with this one storage account up to 100 terabytes of fixed photos without ever running out of space. And the nice thing about storage is you only pay for what you use. So I don't actually have to buy a 100 terabyte system. I can start off, if my app is not very big and not many people actually use it, I might only pay 9 cents for the first gigabyte of usage. If it gets big, then I just pay by the gigabyte per month, a couple pennies, and ends up being a very scalable, cost-effective way that I can go ahead and scale up. Any questions on that? Yeah?
And you can put hundreds of millions of files in the same directory in the blob storage? It's not more like a file system that you might need to sort of ration how many files in a particular directory? How scalable?
It's a good question, yeah. So can you literally put hundreds of thousands of files in a single directory? Yeah, you can actually put literally hundreds of thousands of files in a single, what we call container. And it's kind of a flat system. It's different than a typical directory. So it doesn't have some of the same characteristics of a directory structure. And it's kind of designed where you can literally store, we quote on the website the exact numbers that you can put that we kind of prorate to. And so, yeah, you can actually see the exact numbers. Yeah, it can be literally hundreds of thousands of files. If you ever use SkyDrive, the Windows SkyDrive that's built in, it actually uses blob storage as its actual storage mechanism. As an example of kind of one such service. So if you ever use SkyDrive Windows and you copy a file into it, good chances are it's going to an Azure data center and being persisted in blob storage. The other thing about blob storage I didn't mention here is we kind of do publish with it the semantics of what it supports from a performance perspective. The storage team actually has a pretty good design philosophy, which is they basically quote what they do, and if you try to do more than that, they'll throw an exception as opposed to kind of best effort fix or best effort attempt. And then their SLA includes performance. And so they'll actually say, if it ever takes more than X number of milliseconds to respond on the storage, we will treat that as a failure. So we'll still try to respond, but if we go above, I think it's 100 milliseconds, they'll basically treat it as an SLA violation. And if it goes above that, then they start paying you money back. So it ends up being a pretty dependable system and a kind of a nice core bedrock system that you can really depend on and do some really powerful things with. Yeah, one more question.
What would you recommend in terms of compression? Because if you're paying by the gigabyte, you'd probably want to compress it in your code there.
Yeah, so I mean, the question is sort of what would you want to do for compression? You know, if it's something like an image or JPEG, chances are you're probably not going to get a super amount of compression on top of that, just because the JPEG by default has a sort of a compression algorithm built in. You can get a little bit, but if you were storing like a text file or content like that, that might be a case where you want to take advantage of compression and use it. The other thing to think about just in terms of storage is will you be parsing this or processing this data somehow else? And think about kind of the use cases there as well. I'm going to talk a little bit later on about logging and some of the things that you can do with logging. One thing that's nice about blob storage is we actually support writing our logs to blob storage. So like by default with your web server, we actually write, now actually I'll show you that. This is a new feature we just added on Tuesday. Where if you go into a website, so if you ever go to my blog, all my posts from about 2008 or 2007, the images are actually stored inside Community Server, which is my blog engine, and go there. Before that, what I used to do is FTP up my images to a server that I used to have. And so I have all these blog entries from, frankly, 2005 era that I still need to serve the images myself because I'm too lazy to go back and update 200 blog posts with updated images. And so I have this sort of website here. It's auto-scaled right now, where I actually serve out all my images. And you can see in real time, how much traffic I'm getting. So I get, roughly 300 megabits per second during average load. And what's cool is I can go to the Configure tab now, and as of Tuesday, I can go ahead and turn on my site diagnostics and turn on web server logging, and I can point it to a storage account. And what that means is now every time someone hits something on my website, the HTTP log is actually being written to blob storage in a storage account that I actually specified. And so just sort of an example of where else you can use blob storage. And so if you go to my ScottGoo logs, which is the storage account I'm using right now, the way it basically works is the web server has a different log file that it writes to, and it basically, it's the website name, you can see it, website name, the year, month, date, and then time or hour, and then the server name is basically the log file. And so if you scroll down here somewhere, let me pick a small file. This is basically what it looks like. So if you ever visit my blog, somewhere in here, your IP address and your browser details are now being logged in terms of storage. Going back, this is a long-winded question. Going back to your question of what do you save it in? One of the reasons I'm actually saving this is both so I can get a sense of who people are accessing it, but because it's stored in the blob system, I can now also take advantage of another feature that's built into Azure that we call HD Insight, which is a Hadoop cluster system. And so in the same way that you saw me in part one, I could go and say, create a new database, I can also now inside Azure go and say, create a new Hadoop cluster. And so I could say new data services, HD Insight, create, and I could say Scott website analyzer. I could say I want to have 32 VMs on my Hadoop cluster if I want to be bold. And I could basically point to whatever storage account that I'm storing my logs in are, create this, in about 10 minutes I have a Hadoop cluster, and now I can start doing MapReduce jobs against all my log files for history, and actually start seeing, hey, what time of the day do people access the posts? I could take the IP address and I could map it to countries. There's a public data set out there that's kind of freaky where you can map IP addresses to average income in the neighborhood. And so I could also see, based on traffic to my blog, if I wanted to be really creepy, I could say like, hey, based on your net income, what posts or what technology that I blogged about would you be interested in? And if I want to be even creepier, I could, or not creepy, I guess, if I want to be more capitalistic, I could take that and I could surface ads based on where you are and your likelihood to buy something. And suddenly, this sort of simple set of atoms that you string together, you can start to do something that most websites would never ever think about doing, or at least most blogs would never think about doing. just by kind of piecing these pieces together. And storage plays a big role in terms of being a foundational element that's kind of core to kind of making all that scenario come together. But yeah, you can store lots in it, and you can do lots of cool stuff with it.
Just a quick question before you move on.
Yeah.
Does the blob storage have the same character limit as issues that you get on some file systems?
Good question. The question is, does the blob storage system have the same character limit in terms of path size and things like that? It has some limits. I don't know the exact size limit, but you shoot me a mail, we can find out. But in general, it is fairly kind of flexible in terms of what you do there. So that was a little bit in terms of how I can now start storing my storage and all my images to that file system in the cloud. And now my web tier can scale out. Literally, I can now have, again, terabytes or petabytes of those images stored there. And I now have a much more elastic, vertically partitioned data scheme. We're going to move on now from data a little bit and talk about survival. This is sort of, once you actually start building a cloud app and it starts getting popular, these next set of patterns are really key ones that you're going to want to think about so that A, your customers have a good experience, and B, you don't spend all your time pulling your hair out trying to figure out, when they don't have a good experience, what caused it. And basically at a high level, high point here, you want to think about as you're building any app, but especially a cloud-based app, that given enough time and pressure, everything is going to fail at some point. You're going to have system failures, you'll have network failures, you'll have your app code failure, you'll discover that path that you wrote in the code that you didn't test fully has a failure. And basically, you get to decide as you're kind of building your application, when failures happen, do you have some nice ripcords in place that let you actually fail gracefully, or do you kind of surface it directly to your customers? And when you think about the failures, there's going to be different types of failures that'll happen from time to time. What we call transient failures, which are kind of temporary service interruptions, or kind of enduring ones that require your manual intervention. If you've got a good environment that's automated, you can respond quickly when these failures happen, so that you can make a fix and push it out quickly inside your app. But you'll see, and we'll talk about here as we think about kind of failure scopes, one of the things that's also going to be super important is to understand, do you have insight into what that failure is, so that you can actually fix it. And the next couple patterns will walk more through that and how you can kind of design your apps to handle it. So when we think about failures, one of the things to think about is the types of failures that you might run into. Sometimes it's app code, sometimes it's machine code, so individual machines might fail, so servers might crash and restart. We kind of think of machine failures as, frankly, as fairly common in the cloud world. And part of the design goal of cloud apps is to be able to handle it. And good news is we're already handling that by deploying into websites. If you remember, the website service now automatically, anytime a server fails, it'll pull it out of rotation, stick a new one in for us. And we get to basically get that kind of machine resiliency for free. And that's just built into the core model. Other types of failures you're going to see, though, are service failures. So this is cases where, say, a service that we supply, let's say the blob storage system or SQL database, might have an issue. We have SLAs. We work really hard never to have issues. But given enough time, eventually you'll see an issue with one of the services that we provide. And if you use a third-party service, let's say like Twitter or GitHub or any other service out there on the internet that you call, eventually they're going to have failures too. And so one of the things you want to think about as you're building your application is how do you handle those and be as robust as possible. And there's a bunch of strategies I'll talk about that let you do it. And then you can have kind of what I call the region failure. And this is like literally Godzilla shows up and decides to stomp on the data center. You have a nuclear reactor that melts down that's close to your data center. You have issues where a meteor slams into the region and completely knocks it out, and kind of what I call active gods type scenarios. Generally, you can decide as you're building your application which of these scenarios you want to be able to handle. Machine failures are the ones I'd recommend you always think about and handle. And the good news is we have lots of built-in support for them. Service failures, I recommend you also think about handling, or at least some type of them. Region failures, where you worry about Godzilla showing up or a nuclear reactor melting down, you can handle. They become more exponentially difficult to handle because you sometimes need to think about how do I run my app hundreds of miles apart and simultaneous in an active way. You can, but it's going to require even more work in order to do. We're working pretty hard to try to make that really easy with Windows Azure as well. But as you think about failures and surviving failures, think about these 3 dimensions in terms of how you're going to do it. And know, again, the easiest is the bottom, the hardest is going to be the full region failure. So as we think about failures, the other thing you'll often hear in the cloud world is something called an SLA. And basically an SLA is a kind of a contract we give you where we basically say, hey, we guarantee when you run your app with us, we're going to meet a 99.9% SLA. Anyone ever heard of a 99.9 SLA? A few people have? How many people have never heard of an SLA at all? Okay. But a lot of times when you hear an SLA, 99.9 sounds pretty good. What does it really mean, though? And what this slide basically tells you is this is the amount of time that the service owner is allowed to be down before they violate that SLA. So if you're a 99.9 SLA, that means you can be down 8.7 hours per year. You can be down 43 minutes per month, and you can be down 10 minutes per day. And that just means, hey, I can be down 10 minutes per day, and I didn't violate that nice 99.9 SLA that I gave you. 5 nines basically means you can be down less than a second per day. That's pretty good. Or it's 6 nines. 5 nines is pretty good too. But as you start using services that we provide, or if you use services that other people provide, it's worth understanding the SLA and then translating into what does it mean from within your application perspective. The other thing that I'd say that you want to think about is what happens when your app uses 3 services that each have an SLA. This is sort of a trick question. So if you've got a website 99.95, a storage account with 99.9, and a SQL database at 99.9, what is the combined SLA? Is it the lowest, 99.9? Is it the highest, 99.95? Whichever's failing, yeah? Ah, yes. So here's the trick, which a lot of people don't realize, and then when they do, they gasp in horror, which is it's composite, which basically means it's not the weakest link. It's actually, so it's not 99.9, it is 99.75. Because the likelihood of everything failing conveniently in the exact same window is low. And so if each of these things have failures during the month, that translates into those minutes of downtime, and they happen to be different time periods of the month, your overall dependency, if your app goes down when one of those 3 services is down, it's going to be 99.75. And what you're going to find is at some point your customers are going to say, wow, I want more than 99.75 out of you, which means you as a developer have to think through how do I architect my app so I can survive failures so that my overall SLA to my customer can still be 99.9. And that's where the art and science over the next couple patterns will start coming into play. Make sense? And one of the things I just mentioned about SLAs before you say, my God, this means if I go to the cloud, I'm always going to be down 2 hours a month. SLAs are kind of legal contracts. Like when we violate them, we have to pay you money. It doesn't mean that we guarantee that we're going to be down that much each month. And so every service aspires to be much higher than its SLA. And I would say for Azure, we tend to actually do much better than our SLA. But just as an app developer, this is something for you to think about as you build your apps. It could be this bad. And still be in contract. And so again, you want to do some of these patterns I'm going to walk through so that you can actually survive this, and your customers will never know if a service you depend on is actually down. So how can we design with some of this stuff in mind, knowing that things are going to break on us on a certain basis? Part of the reason in part 1 I talked about having an automated environment where you can react and deploy quickly is that actually is P0. The first priority to get right is the ability for you to react quickly when things break, because you're never going to be able to anticipate everything. But there are a couple patterns that you can also integrate that you can anticipate the types of failures, and if you build into your application up front, are going to make your life a lot easier. And basically, there's going to be 5 that we're going to walk through today. First one is have really good monitoring and telemetry built into your system before things start breaking. The worst thing in the world is to know that something is breaking inside your app and you have absolutely no visibility into what it is. And so we're going to talk about how to do that. We're going to talk about handling transient faults. We're going to talk about using distributed caching. We're going to talk about a concept called circuit breakers, which is pretty cool. And then we'll talk about loose coupling using what's called the queue-centric work pattern. So step 1 here is monitoring and telemetry. Anyone here remember Frogger? It was a great game. I hope it's on the Xbox One. I don't think it is, but is it on Xbox 3D? Okay, cool. So This is, if you remember this game, the goal is to get across the street and you got to dodge cars and logs and a whole bunch of other things. This is what running a cloud service looks like when you have good logging and telemetry. When you don't have good logging and telemetry, all you see is yourself as the little frog, and you have no idea which car is going to hit you, or even which direction the car is coming when it hits you before it hits you. And so, just meta think of it, if you know everything that's going on in your app, and you know that you can quickly pinpoint which log is going to come at which point, you're going to be running in a much better way. And the best way to do that is by implementing logging and telemetry in your system. There's a couple different ways you could do logging and telemetry. I'm going to show how you can actually write code to do it. The other thing I'll kind of mention up front is it's really easy to kind of rent or buy a solution. And there's a bunch of kind of great partners that we have with Azure that have integrated with Azure. And I'm actually going to show you one of them, which is New Relic. And the cool thing is, for basically like $40 a month, you can actually have a fairly decent telemetry system out of the box without having to write any code, which is kind of cool. And so one of the things to think about is if you don't have time to invest in writing a telemetry system, or you've already gone live and you're starting to see issues, go sign up for a month of New Relic, and until you actually instrument your own app, you can actually get a huge win out of it. And I'll kind of show you up here how it's done. It's got, so I'll post these slides obviously, but Scott Hanselman also has a nice URL for how to set it up. You're never going to remember that URL, but it's embedded in the slide, and so you can actually look at it afterwards. And so what I did here with New Relic, they're a pretty cool SaaS vendor. They're integrated within Azure, and so what you can do is you can basically go in Azure and you can say new store, and we have a bunch of third-party services that are integrated as part of our portal and overall billing experience. And so what you can do is you can say New Relic, somewhere here in this list under in, click next. They have a free version that you can use forever. They also have pro versions that you can use depending on how many VMs and what type of resources you want to do. So basically you just go ahead, click, you hit next, next, and 30 seconds later you have New Relic set up for your Azure subscription. And we'll basically bill you, it just gets added to your Azure bill, so you don't actually have to give them your credit card, and so it's a really easy way you can sign up for a subscription. Once you sign up, it'll show up in the portal, just like a database or a website. There's a connection string, don't look at that, which is mine, that you can basically copy and paste. And then all you need to do is go into your ASP.NET app, or any .NET app for that matter, and you can right-click and add a NuGet package, and there's a New Relic NuGet package. As part of installing it, it'll ask you for the key. You paste in that key that you grabbed from the portal into it, and then deploy. And that's it. And actually, there's one other thing you got to do, which is you do need to go ahead and in your website, you just add 3 app settings. And under it, my little config file here, I lied, it's 4 app settings. You can see here, these are the 4 settings that New Relic also looks for. One thing you'll notice here is it is turning on the CLR profiler, and it takes advantage of the CLR profiler to actually do some diagnostics on your site. Does anyone know what COR stands for? A little bit of trivia. That was actually the name of the CLR before it was called the CLR, and for whatever reason, we forgot to update the string. So anyway, brought back memories there for a moment for me. So anyway, then you go ahead and redeploy your app, and then, so let's go ahead and hit this app a few times. So we've added some stuff. I can look at fixes and things like that. And then what I can do here is just go into my admin tool inside here, and if I click Manage, I'm going to do single sign-on from Azure into the New Relic admin tool. This will show me all of my apps that I'm running inside Azure. And if I click in here, you'll notice without having to write any code, without having to change any code in my app, I now actually can see how my app is running inside the New Relic admin tool. And so I can actually see the throughput in my server. I can actually see a lot of people from Australia are hitting my site. And I can actually see average latency times from the browser to the server in terms of how long it took for the HTML pages to render. And how long it takes the JavaScript, how long it takes. Notice my server on average is responding fairly fast, between 133 milliseconds to a peak of 534 milliseconds. And if I want to go even deeper, I can drill in, and it'll actually even show me, if I go to say, oh look, someone outside in the audience is trying to log in with Google. If I go to task create, it'll actually even show me in my code where CLR-wise or any .NET-wise, where I'm actually spending my time in the server-side code. And so it'll actually show me literally profiler view of my code in real time running in production. If I use external services as well, so for example, notice I'm using blob storage. It'll even show me my performance, how many calls I'm making to blob storage in a particular point in time, and what the average latency response was. And it's pretty cool. I didn't have to actually write any code to do this. I literally sign up for free, run the NuGet package, paste it in, and away you go. And you actually have a fairly decent monitoring solution with the free tier. The pro tier even lets you actually, it'll profile all your SQL calls and actually tell you how much time you're spending in your database, which SQL calls are actually costing the most time. And it's kind of a nice, pretty easy way that you can get a whole bunch of instrumentation literally without having to do much effort out of the box. So check that out. We work pretty closely with them, and they're a great Azure partner that kind of integrated. Now, once you actually have one of these solutions that gives you kind of an out-of-the-box rough view, you start to have a little bit more insight into your application. But what we're going to do now is walk through how we can add even more insight so that we can actually, when we tell, hey, things are taking a long time, we can actually go that next level detail down, which is to understand what was the use case that exactly caused it. And that's basically where logging comes into play. And at a high level, think of it in terms of log everything inside your app. Would be kind of the one takeaway. Because if you didn't capture it in your logs, when someone tells you something went wrong, as far as you're concerned, it didn't happen. There's really no way to tell after the fact when someone says, I tried to log in last night and it was slow. If you didn't log it, you're going to have no clue why. And if you did log it, then you can actually pinpoint fairly easily and fairly quickly exactly why and where and which resource you depend on that might have been causing the problem. A couple things I kind of recommend is every time you call an external service, so every time you call blob storage, every time you call a database, every time you call Twitter or anyone else, always log whether it succeeded, and if it succeeded, how long it took. Those two things will let you pinpoint so many of the dependency problems that you might have inside your application. And it's, again, fairly easy to do if you do up front, and it can save we say save your bacon. I don't know if that translates well into Australia, but it can really save your hide anyway when you run into a production problem. So here's a simple way to do it. So I have some data access code here where I'm basically using find task by ID async. And this is basically the code that's going to go ahead and return that task, and then I return it. You'll notice that I've added a bunch of error handling and logging code into it. And what am I doing here? One of the things you'll notice is before I make my call to my database, I'm just going to instantiate a standard .NET diagnostic stopwatch class and start it. And then when I finish calling back from my database, I'm just going to stop that time span, and I'm going to write to my log system and say, hey, we called the SQL database. Here's the method I called. Here's how long it took. And by the way, here's the ID I searched on. And that one simple statement, just by adding it there, means that every time that my SQL database has a problem or takes longer to return, or someone comes in and says, hey, I searched for my item and it just seemed to take forever before it showed up, I can now go to my logs and I can say, okay, at 10 o'clock, you searched for it. What was happening there? Was it a one-off thing? Did SQL slow down for a while and then pick back up? Just by capturing that timing information, I can now pinpoint exactly what happened and if it went wrong. And if an exception occurred, so in other words, maybe it didn't just take a long time, maybe it eventually returned an error, I'm going to make sure I log that as well so that I actually have details about the full exception that occurred captured in my log system.
Does that Logger API have implemented timestamping?
The question is, does the Logger API implement timestamping? You certainly could do like a using statement and wrap it so that you could actually kind of say, once you break out of the using statement, automatically log. For this purposes here, I basically just did it kind of manually like so. What you want to be able to capture is not just how long it takes to log it. You really want to make sure you capture before the operation and then after the operation. That's why I kind of have it as an explicit statement as well. That makes sense. One last thing, don't log secrets. If you have a check-in security system and you log the password of the user logging in, and you hash your passwords in the database, but your log captures the password, you just made your system incredibly insecure. So anytime you've got a secret, be careful not to log that, but try to log everything else around it.
Is logging asynchronous?
Yeah, the question is logging asynchronous? It can be, and the default system diagnostics is. So yeah, logging should be asynchronous if you implement it right. A couple other things about logging. How many people here have logging inside their applications today? How many people here are used to turning on logging when there's an issue? How many people run logging always on inside their application? Cool, okay. In the cloud world, what I recommend is always run with full logging on. Probably not verbose, but have error warning and info level logging traces turned on. And you might say, my gosh, that's a lot of data. And the answer is yes. The good news is it's all going to the storage system where you can store petabytes of data. And you can always go in and say, hey, after a month, I'm going to delete my old logs if I want to go ahead and save stuff. But the cost of actually storing a bunch of trace statements versus the time it will save you as you debug issues, believe me, it is worth that extra $3 a month that you'll pay in order to store all of those log informations for the month. And in general, I would say try to log as much as possible inside your application and keep it always on. Not just when there's issues, but keep it always on. And you can basically have a gold mine of information that you can go ahead and pinpoint accuracy problems. Built into most of our compute containers in Azure are built-in logging support. So websites, for example, supports a system diagnostics listener that automatically logs to storage today. It also, I showed a little bit earlier how you can wire up the HTTP logs to go directly to a blob or to a file system as well. Cloud services, which is another one of our models, does the same. Storage also has what's called analytics, which also go ahead and do metrics and logging information as well. So let's go ahead and take a look at this in action. So basically, the approach I'm taking here, and you'll see this inside, say, all my data access code, is basically just like what you saw in those slides. Every single time that I go to do an operation with an external service, I say, start the stopwatch, do the thing, stop it, and then log it. And one of the things I've done on my logging implementation is I pass it in as a iLogger interface to all of my classes. So I'm using dependency injection in order to insert it. This is what this iLogger interface looks like. It's a very simple interface with just a couple of methods. And my default implementation that I'm doing here, I just implemented in a logging project, basically just calls the standard system diagnostics trace API. So it's a fairly thin API. And you might ask, why not just call system diagnostics directly? You could. The one nice approach about this, though, is it means that if I ever want to add richer logging infrastructure, I can very easily add it behind that interface and still kind of get in between system diagnostics and it. If I tie myself to a specific logging implementation and I decide, oh, I don't want to use system diagnostics, I want to use inlog or one of the other kind of logging implementations for .NET, I'm kind of bound into a corner. I got to rip out the logging infrastructure everywhere. Doing that simple interface gives me options down the road, even if I'm just using system diagnostics to begin with. And then what we're doing inside websites is, and you can kind of see this reflected if you actually look in your portal here. If we pull up our Fix-It project and look in the Configure tab, you'll see that I can go ahead and, there it is, turn on both application logging. Where does it say off? That's weird. Oh, here it is. It's on. Sorry, that's a different thing. I can basically turn on application logging. I'm logging information and hire. And then basically I just point it to my storage account right here in order to persist it. And what that means now is I can go back into VS. I could go ahead and drill into my storage account. There's my table. And if I click this, you'll actually see all of my trace statements over the last few hours for this application. And you can see they're all information level, so there's no errors that are popping, which is good. And then if I double click on any one of these, you can see here, this came from my Fix-It task repository. And you can actually see drilled in here, that's how long it took in terms of milliseconds. So it took about 41 milliseconds to process this particular SQL query. And if I actually go to the right, I can actually see, someone named Adam in the audience looks like created this and actually uploaded an image. And so I can basically see, he did it, that's how long it took, that was the time it took. And if there was an exception, it would be captured. And so that's now all captured inside my logging system. You'll notice here I also then for blob components, I have a component type here called component blob. And you can see likewise, every time I upload a photo now, I'm likewise also capturing how many milliseconds. In this case here, it took 2 seconds, mostly because I'm uploading a large file across the Atlantic or Pacific. That's how long it took for that to go ahead and actually come back. So, simple way you can start logging everything. Once you have this, now anytime someone reports there's an issue, you can immediately go to your logs, you can pinpoint the time, you can see what services were failing, and you have a much better sense of actually what's going on inside the system. If you want to get even fancier, because this is stored in the storage system, you could spin up a Hadoop cluster, and you could also, or you just run a standard log parser tool, you could also look to see how does the variance happen on my service. So my SQL database on average is 2 seconds, or no, it's not 2 seconds, it's on average say 10 milliseconds for queries. Are there times of the day, or are there periods during the month when it actually goes up to 40 milliseconds? Does it go higher than that or lower? You can actually start doing real analysis on your app and start to really understand your dependencies in a much richer way than just is it working or is it not. And if you store your logs for months, you can also look historical trends to actually see how your services are handling based on load and usage. Yeah?
Where you're starting the stopwatch manually there, would you consider writing a wrapper for the task and doing it?
Yeah. You certainly could, yeah. The question is, would you consider like writing a wrapper? I think the stopwatch thing, a few people asked about that. You know, it kind of looks a little hokey. I've added it both for clarity and then also it does give you a lot of flexibility where you can start it, call a bunch of stuff, and you can kind of choose if it's an error to do something different. But absolutely, you could go ahead and write kind of your own little wrapper, or you could put it as an attribute and make it declarative. So definitely go ahead and implement logging throughout your app. Take advantage of the built-in diagnostic system. Literally in just a matter, you know, if you use system diagnostics just as is, literally in a matter of minutes, you can have a full instrumentation system set up within your system. So next type of pattern. So once you now have diagnostics, say New Relic, and then you have logging, you have a whole bunch of insight into how your system's doing. And with New Relic, and we also have a built-in feature in Azure, we can even send you an email every time we start to see your system fail, so that you can set thresholds for alerts where we'll actually proactively notify you when something bad is happening. And so then you can go to the logs, you can drill in, you can figure it out. You'll start to see lots of interesting insights when you start looking at your logs about things failing and services that you depend on that you're kind of surprised, wow, I didn't know that failed. Why did that fail? And as you drill in, you'll start to see different types of patterns of failure. One of the patterns you'll probably see is something we call often transient faults. And these are things that happen occasionally. They usually are self-healing, so they don't require usually manual intervention. They can be kind of just blips, so one-off things. And sometimes they can happen a little bit more frequently or be a little bit more persistent. Why do these things happen? They happen in your production environment as well, but you might just not be logging it and not knowing it. They do happen a little bit more in the cloud world for a couple of reasons. One is, in a cloud world, you tend to actually be running in an environment where your database and your web server might not be sitting exactly next to each other on a single network. You might be going through a router somewhere. And so you'll start to see connection failures where the connection gets chopped because a load balancer restarts, or you kind of dynamically remux somehow. And so you'll start to see a couple of those types of connection failures pop up a little bit more frequently than if literally the database server was 10 feet away from your web server. You'll often, if you're also calling other services, you'll see kind of what we call busy signals, where the service says, hey, I'm being hit by a lot of people right now, come back a little bit later. And you want to be able to kind of handle a retry on that. And you know, the goal with kind of this transient failure kind of semantics is be prepared if that thing fails for some reason. How do you retry, and how do you retry in a graceful way before you give up and fail yourself? And there's a couple different ways you can do it. One is by having what we call smart retry backoff logic. And that basically means I call you, you say, sorry, I failed, and I'll say, okay, I'm going to wait a second and I'll try it again. And if you fail again, I might wait 3 seconds and try it again. And then after 3 seconds, if you still fail, I'll say, screw it, you're having a problem, I'm going to return an error back to my user. But just having that little retry logic, and once you look at your logs, you'll start to see it, can actually save you, because about 95% of those types of cases, if you try a second time, will actually work. And that can dramatically lower kind of what your customers are seeing as failures just by implementing that logic inside your system. A couple of ways you can do this. We have a cool patterns and practices library called the Transient Fault Handling Application Block. And what this does is basically there's a different kind of policy engine that you can set using a generic. And so in this case here, for SQL, I'm going to say every time I do a database call, retry up to 3 times, and basically make sure that those 3 times happen within a 5-second window. And this way, you create a connection. Every time you do your SQL operation, if for some reason SQL closes the connection or throws an error, it'll try, and it'll do an exponential retry back off so that it's not constantly hammering the system right after each other. If you're using Entity Framework, with the new Entity Framework 6 that's coming out, it has built-in support for this type of retry transient logic as well. You can basically add 1 line of code inside, actually it's technically it's 3 lines of code, inside an EF configuration class. And that basically just says, equivalent thing that you saw on the previous slide, but now just applies it to Entity Framework. Every time I try to persist or retrieve something from SQL, if it fails, try up to 3 times, but make sure it takes no longer than 5 seconds. And so once you configure that, then any of those kind of transient failures that happen on the wire, your app code doesn't even know about it, as long as it doesn't take more than 5 seconds. If it takes more than 5 seconds and you're still having issues, EF will throw an exception, and then you can decide how you want to handle it for your users. Code I was going to show is basically the same code in that previous slide, so we'll skip the demo just in terms of time. So a couple of times I mentioned, though, this concept I call exponential retry logic, or exponential backoff logic. Anyone have any idea why that might be useful? I kind of cheated and I showed you a slide of people queuing in line. Mostly because if every time you fail, you just keep trying and keep trying and keep trying, if 10 people are all trying to do it and more people keep coming and everyone keeps hammering on the system, you basically are effectively causing a denial of service on whatever you're actually trying to connect to. And so if the logic isn't smart on the clients to kind of gracefully back off, you can end up making a transient issue much worse by effectively having lots and lots of clients go ahead and completely hammer the system. I remember a couple of years ago when Skype went down for like Christmas. This was actually, by the way, before Microsoft bought them. I went to dinner with the guy at Microsoft now who runs Skype, and he was telling me about this terrible Christmas he had. We were trading war stories of issues in the cloud. And you know, Skype went down for a pretty long time. It was almost 48 hours. And part of the reason was they had a bug in their retry logic. And so what happened is a small glitch of the Skype receptor being down. Suddenly, you know, the 1,000 customers that were trying to connect to it, instead of saying, okay, I'll try again in a minute, they just started going into basically an infinite loop, hammering the system. And that basically meant the Skype receptor never could get back up. And then it cascaded to other receptors. And then basically Skype got into a model where their users were attacking them. And everyone that was trying to use Skype was basically doing a massive, the world's biggest denial of service attack on all the Skype infrastructure. And that can happen. And so, you know, likewise, if you've ever missed a flight, it really sucks when they say, I'm sorry, we're bumping you. And you always say, but there's a flight that's coming in a few hours. Can't you get me on that? The reason to bump you is because if they put you on that flight, they're going to bump someone else, and the problem just gets worse and worse. And so sometimes the reason to always cap the maximum number of times you retry is sometimes it's just better to fail and get out of the way and make the user come back again later than it is to just continually hammer the system and have a denial of service attack. So that's a little bit of transient fault handling. Just a few lines of code there can actually fix probably 80 or 90% of the types of failures that you'll see in these types of distributed systems world. So definitely go ahead and add it, and it can handle it. Next pattern here I'm going to talk about is distributed caching. This is another one that is often not that difficult to implement and can have a dramatic performance, or dramatic both performance impact, but also availability impact within your applications. And so what is distributed caching? Well, at a high level, it's not always practical to hit every data source on each request. Sometimes as your service will start growing, if every time you need to hit the weather service for every one of your users that visits your site, because you want to service what the weather is in their location, as your service becomes more popular, you're going to throw more load on that weather service. And at some point, that weather service is going to say, look, I just can't handle your load. And so what you really want to think about is, hey, can I cache it so that instead of on every user or every request hitting it, can I cache the data and maybe only every 5 minutes hit it or every 30 seconds hit it? That is a way you can dramatically lower the threshold or throughput on top of that system. Other things to think about is data doesn't always need to be immediately consistent, even when things are working well. So that weather service or stock data, unless it needs to be a real-time system, 1 second or 1 minute granularity of accuracy is probably good enough for a lot of those scenarios. And again, that can dramatically lower the amount of traffic that you're going to put on a particular resource. And then the last one here is sometimes when things go bad, if you have a cached copy of data that you can fall back to, it's a really nice cheat where you can make your users think that your app is still working and functioning fine, even if something it depends on is completely on the floor. And this is something I'll talk a little bit later called a circuit breaker, where if you use caching in a smart way, you can fall back so that your app automatically detects, hey, my database is down, let's go to the cache copy. And you can at least provide a degraded user experience to your customers, as opposed to kind of throwing a fail whale or an error message that says, sorry, we're completely down. And for people that, any people who use Twitter, remember a couple years ago when the fail whale always showed up? And it was fun the first time, and then when it happened every minute, it was really annoying. That's an example of when things aren't working, you kind of, just tell the user, I'm sorry, we're having a bad day in the office. And customers tend not to like that. If you use Twitter recently, when Twitter has a problem, you'll notice it degrades to an experience. So it'll actually show you, hey, we'll show you the last 20 tweets. We won't show you the last, you can't go beyond the last 20 tweets. And the user says, well, okay, that's 80% of why I go to Twitter, so I'm okay with that. And that's an example of degraded experience. That's a case of using smart caching to kind of fail over so that your users can actually get at least a better experience than they would of a complete failure. Cool thing is we just launched a new service 2 days ago, or yesterday. It was 2 days ago, yeah, yesterday. We call it Windows Azure Cache Service. It was 2 days ago in the US, but that was yesterday here, so it's confusing because of the time change. But called the Windows Azure Cache Service, which makes it really easy to implement distributed caching within your applications. It's high throughput, low latency distributed cache. So it's, when you store something in the cache, it's not written to disk, it's stored in memory. And it's built with a scale-out architecture so that we can keep adding servers and we can make it look like it's one giant cache that's storing hundreds of gigabytes of memory. And you don't have to worry about the fact that it's scaled out across multiple servers or how it's partitioned. We do that partitioning for you. And it basically is a very simple key value programming model. Get something, put something. And it's basically an average of about 1 millisecond end-to-end latency when you get something, and it's about 1.2 millisecond latency when you put something. And that get and put are going over the network, so this is about persisting it across multiple machines. And you can basically start with 128 megs of cache and go up to 150 gigs with the preview that we just shipped yesterday. Implementing it's really easy. Go to the portal, new data services cache, pick where you want it to be and what the size offering you want. It then provisions in a couple minutes. You can then drill in and see a dashboard view of how much you're using. You can go to the configure tab and you can control what are called partitions or named caches, where you can have different sections of your cache have different policies. So for example, you could say, I want to have an absolute thing, things that only last 10 minutes, no more, no less. You can say sliding, so they kind of gracefully grade out. Or you can say never cache this thing out, never fault this thing out of memory. And you can have different policies, and you just sort of, the get and the puts, you just name the cache you want to go against, and that policy will be enforced. And then to program against it, you just go manage keys, just like the New Relic thing. You grab the key, you go to VS, you install a NuGet package, in this case Windows Azure Caching. You paste in the key and the URL into your web.config file, and then you can write code like this to basically put a key and a value into your cache, and then you can get it back as a string or whatever other object that you want. So a pretty simple way that you can go ahead now and literally cache anything you want inside the system. There's then monitoring, so you can actually see how much memory you're using inside your cache, what the access patterns look like. You can then choose to scale up or scale down the amount of memory that you use within your cache. So if you're finding, hey, I'm filling up my cache quite a bit, and I'm constantly evicting stuff, I can just use the slider and I can get more memory if I need to, or I can go in and debug why I'm using so much cache. And it basically scales up and scales out. And basically the way this system works is kind of nice. I can have my website VM, so my websites that we're already using with our auto-scale system, they can all share the same distributed cache. And so what makes a distributed cache different than, say, the ASP.NET cache, which is an in-memory cache that we've supported for a while, is that every time you write something to the cache, instead of storing it on the VM, it's going to write to the cache pool. Inside there are VMs that we manage for you automatically, and it's going to distribute that cache across those VMs. And when you slide up or slide down the amount of capacity you need, we dynamically add and remove virtual machines for you for that cache. And so we can make it look like one giant 48 gig cache, even if it's implemented across multiple servers. What's also nice about the cache is if we ever need to patch the VM, we move all the items from the cache to another machine, and then we recycle and patch the machine so that you never actually lose the cache entries. We also have an option where if you want to, you can store the cache on a single value in multiple machines so that you can survive even if a machine crashes, your data will not be lost inside that cache. So an easy way you can start to actually take advantage of a cache, spin it up, and now within a few lines of code, you can use it from within an ISVM, a website, or a cloud service. What you can then do inside your app, a couple common patterns for caching. The first one is something called an on-demand cache-aside lookup. That basically means this is probably the one that a lot of people here probably used before if you're using the ASP.NET cache. You go hit your database, you get the return contents, you stick it in the cache, and then you render your page. The next request, you first check the cache, and if it's there, you process it. Otherwise, you hit the database and you stick it in the cache. And that way, basically, you're hitting your service, and then you're effectively caching it in a look-aside kind of way. Other pattern you can use is what's called a background data push. In this world, your web tier could always be going against the cache for its data, and then you could have a VM behind your service that's non-interactive, the customers don't hit, which is periodically hitting your data and then pushing data into the cache. And what that means is your web tier is always going against a 1 millisecond latency lookup cache, so it's always lightning fast, and then your background service just basically populates your data in the cache on some regular interval. If you have a service that goes down a lot, or you have something across the internet you're calling that's very, very highly latent, the nice thing about that lookup model is your users that are actually accessing your site will never see the fact that it took 2 seconds for that request to actually return across the world. The background cache is the thing that's actually doing it. Your users are basically seeing the experience of when your web tier hits the cache immediately and it renders back instantaneously. And so it's kind of a nice model you can use to make things a lot faster. And then this third one I just threw in here is something called a circuit breaker. And this is basically where, if you want to, inside your app, you could instrument it so that if suddenly your database is starting to throw lots of errors, that's where you could fail back to your cache of cached content that might be, again, managed either by a look-aside or a background data push, and you can start to serve things out of your cache as needed. And so that's, again, a way you can cheat, like that kind of Twitter example I talked about, where you can fall back and actually have a degraded user experience. It might be something you tell your users, we're having a problem, here's some old data. Or it might be something you never even tell your users that it's actually failing. You just take advantage of the fact that it's cached, and you can basically have still a decent user experience without them being impacted. In high level, I highly recommend using distributed caching in any app where your users share a lot of common data. So if you have a product catalog, use a cache. If you got content like a CMS system, use a cache. Because you're going to find the performance is going to get a lot better, and it's going to insulate you if the actual underlying data source that's storing the catalog or storing the CMS content ever goes down. And if the content doesn't change that frequently, even better, go ahead and use the cache. You'll find it's not very expensive. Right now, if you create a 128 meg cache with the distributed cache service, it's $12 a month. Again, we pay by the minute, so you can, we actually charge by the minute. We don't pay by the minute. And so, if you want to use it and try it for dev test, it's really easy to get started and start taking advantage of. And again, it can dramatically improve the reliability and the perceived reliability of your application. So that's really good for read-only content. So if you got any scenario where you got read-only content where you can cache, go ahead and cache it. But what about scenarios where you actually need to do work? So say, for example, our quick fix-it app, when I actually go ahead and submit a new fix-it, I can't really put that into a cache because I need to somehow write it to a persistent data source in order to process it. So how can we handle that? And that's where this last pattern comes into play. I call it the queue-centric work pattern. Actually, many other people call it the queue-centric work pattern as well. I didn't make up that term. How does the queue-centric work pattern, what's it for? Basically enables it's called loose coupling between, say, a web tier and your backend tier, or frankly, any other tiers within your applications, by asynchronously sending messages through a concept we call a queue. It's useful anytime you're doing time-consuming work. So if it's something that's going to take a couple seconds to do, rather than block the end user from success happening, just stick the thing into a queue, tell the user, great, we've done it, we're working on it, and then background process it with a queue listener, and that way you're not blocking. Anything that's high resource intensive, stick it in a queue, and I'll talk through why that helps later. Anything that requires an external service that might not always be available, stick it in a queue. And if you want to be able to protect against sudden load bursts, stick it in a queue. And that's something called rate leveling. Anyone here ever bought something on Amazon.com? And when you go to check out and you hit submit, are you always amazed by how instantaneously they do your credit check and they actually ship it? You hit submit, boom, thank you for your order, it's on its way. It's not really on its way. What they did was basically they stuck something in a queue, and then they told you it's on its way. And in the background, they're processing, doing the credit check, pulling the thing from the warehouse, scheduling it with the shipping company, and then it's really on its way. And that's an example of the queue-centric work pattern in action. The only trade-off is, it does mean that the end-to-end time can sometimes be actually longer than if you did it synchronously. But in most cases, and for most scenarios, like the Amazon case or like some of the other cases we'll walk through in our Fix-It app, the actual benefits far outweigh that cost. So let's think about this Fix-It app that we've been working on and put an example of this in concrete action. We got our Fix-It web server right now running as a website that's hitting our database. And when you go to the website and you say, I want to create a new Fix-It request, and you submit that form, it writes to the SQL database. And it writes to the blob store, and then it says success. Now, if the database is down, though, what happens when the user submits a Fix-It request?
Error.
Correct, error. And so basically, today we're just going to say, whoop, sorry, come back again later. And that basically means we're telling our customers we don't have a very reliable service. So what we can do is move this to be a loosely coupled model with queues, where instead of writing directly to the database when someone submits a Fix-It, we're going to instead write to what's called a queue, like a task queue. And we're going to create a little message. We can put a little JSON payload. And when someone places a Fix-It, we're going to go ahead and stick it in the queue. Notice we actually are now saying success immediately, just like Amazon does when you hit submit and say, hey, your order is now done. We reply immediately, success, everything's great. And that's because we persisted this task into a queue. So we know that even if the power goes off in the data center, our task will still be there when the power comes back. We run in 5.9 data centers, our power doesn't go off, but if it did, it would still be persistent. And then basically what you do is have a background listener that's going to pull the message from the queue, process it, and then basically write it to the SQL database. And what this means is if the SQL database goes offline, in fact, even if the queue listener goes offline, our users can still go ahead and submit messages, and they'll still see success. They'll just queue up inside the queue. And then basically when the system comes back online, it can go ahead and catch up and process all those messages. So it's a simple kind of pattern there that we just introduced. Dramatically improves the availability of our application. It's also then useful for what I call rate leveling. So this is a case where, let's say you suddenly get a lot of traffic all at once. You can actually start dumping all these messages into a queue. You can use the auto scale to scale out elastically on the front end and automatically handle any number of web servers in order to submit all these orders. And then your background services can go ahead and just go ahead and process them as they come in. And you might have 3 web servers but only need 2 background services. You can now scale these independently. Or if it's your web servers are fairly logic independent, you might only need 2 web servers, and you might need 10 backend services if you're going to run a large compute task in the background. And the beauty is by kind of decoupling the 2 sides of the equation, you can now scale each of those independently in a very smart way. Cool thing about autoscale is it doesn't just work with websites. You can run autoscale on virtual machines, or what we call worker roles inside Azure. And so you can scale up and scale down the number of VMs processing things based on the CPU of those worker roles. You can also, and this is a really cool feature of autoscale, is you can set it up so that we can scale up and scale down the number of VMs based on how many things are inside a queue. And so what you can do is you can tell autoscale, try to keep no more than 10 items inside this queue. If it ever goes above 10, start spinning up more VMs to process it. When it catches up, start shutting down the VMs. And so you can have auto scale happening, not just on the web front end, but also on the back end side as well. So how hard is it to do this? Good news is it's not hard at all. We got our website here, clean room, my room's a mess. We do an image, we hit submit, and we show success. That's kind of the experience people see today. Now right now, the way this works though is we're always inside. When you create a new task, we're writing directly to the Fix-It repository. If you remember that code from a little bit earlier. So now, and then we show the success page. So now if our database is down, we're going to have an error here. What we can do is change it to be this, where instead of using our repository for the database as part of the create task, we're instead going to use this Fix-It queue manager and send a message. It's the exact same POCO object that we used with our EF repository, but the way this code's gonna look is it's gonna basically talk to our storage system, which has a concept of queues. It's gonna get a reference to the fixit's queue. It's gonna serialize that fixit POCO object as JSON, and then post it into the queue. And that's literally all the code necessary to kind of swap it out so that now I'm posting something into the queue. And then I'll just have a background listener that looks like this. And what this is gonna do is just basically loop forever, pull messages from a queue, deserialize the JSON, and it's using the exact same EF repository that we used before in order to actually write it inside the database, and then it deletes the message. And you'd probably add a little bit more error handling logic and other things, but this gives you a simple example of what a pseudo backend queue listener would look like. And just with those a couple extra lines of code now, I can scale up better. So if that fix-it task required a lot more computation, I no longer block the person from sending it. And now if my SQL database goes down, I'm no longer blocking people from submitting new requests into the system. So what does this bring us? So I talked about the resiliency. If it ever is unavailable, it lets us add much more background logic. So if we needed to, once the thing was in the system, go ahead and figure out, okay, who's his manager or who's on call in the system, and hit a lot of other services, we can now put it behind this facade, and we can actually do a lot more work in the back end without actually blocking the UI thread and the user seeing that submitted. We could send SMS messages and emails to kick things off. And this gives us a lot more resiliency. If the SMS service is down, hey, we can actually just process everything else and then stick something in the queue for SMS and just have another queue for SMS. When the SMS service comes back up, we can then send the SMS message. So again, you can start to stitch these things together in a very nice way that can add reliability across the system. And then best of all, what does this do for reliability? So previously we had 99.95, 99.9, 99.9 for a composite SLA for this create fix-it scenario of 99.75. So if we introduce the queue, we now only have two dependencies because our storage system, our queue actually runs on the storage system as well, and so they actually share the same SLA. And so now, if the database is down, it doesn't matter. I can actually raise my composite SLA up to 99.85 just by sticking the queue in the play for that fix-it scenario. So only a couple lines of code, we've now improved it. Now you might say, 99.85 is still not something I can go ahead and sell my boss. I want to have 99.9 for my app, or I want to even have 99.99. How would I do that? Well, a couple things you could do. Have two queues. So if your system requires a queue, don't just have one queue, have two queues and put them in two regions. So for example, once Australia comes online with Azure, you could have a queue in Victoria, you could have a queue in New South Wales, and your web tier could try the main queue in its local region. If it's having any problems, just go ahead and post the message to the queue a couple hundred miles away. The likelihood of both of those queue systems being offline at the same time is very, very small, which basically means now our SLA went from 99.85 to probably 99.95, since the only dependency now is on the web tier to actually be operational. If we wanted to go even further, we could actually have two copies of our web tier running in the Victoria region and running in the New South Wales region. And so we basically just deploy our website in two places. We have a cool feature inside Azure called the Traffic Manager, and we can automatically send people to one or the other depending on where they are in the world, or you can automatically fail over depending on if one of those web tiers is having problems. And suddenly, that 99.95 service probably just went to four nines of availability, which is higher than probably pretty much every website out there in the world. And so you can start to see kind of these ways that we can start piecing these pieces together, and we can go from a system that's occasionally going to fail. Once we add the instrumentation, we know why. Handle transient fault handling. We start doing smart dependencies with caching and with queues. And once you have multiple copies, you can suddenly take that system up. And once the traffic manager and the multiple queue thing is in play, we could literally handle that scenario where if Godzilla comes out of the water and stomps on our data center and destroys it, your app is still ticking and your customers would never even know if it went down. We do have, and I'm not going to go into too much detail since I have 20 seconds left in this talk, a feature called Cloud Services, which is a way that you can take that website that we were working on earlier, you can convert it to a cloud service. And with a cloud service, you can have both a web tier and a backend tier composed as one. Alternatively, you could keep the websites the way it is, and you could spin up VMs or just have a cloud service of worker roles running in the back end. It's a great way if you want to have non-interactive or non-UI processing logic that you can bundle it up, and we provide a kind of a nice management experience around it, also directly inside the portal. So we covered lots of stuff this talk and the past talk. I think I said we'd start easy, and towards the end, your head would probably start to melt. I hope it melted a little bit along the way. But these sort of 13 patterns, each one is not that difficult. Hopefully I gave you something to think about. Hopefully you learned something new. When you use them all together, you can start to build really reliable and robust applications. They're not that hard to use. In most of these cases, it's just a couple lines of code. A lot of it's just knowing that you should be doing it. Once you put them all together, you can build great applications that can literally scale to pretty much any size. We've got customers that do hundreds of millions of page views per day. We've got customers that store hundreds of petabytes of data, and we've got customers that process, just intense amounts of information. And if you adapt these patterns and use these patterns, you can be one of those too. And the great thing about the cloud is you pay only for what you use. So you could basically use all these patterns and run a site literally for free on Azure at no cost. And then as your traffic grows, you actually start paying a little bit more money. But with things like autoscale and the elastic blob system that we have, you really end up paying a ton of money. And it literally is only as your business is growing that you actually have an expense. So follow these cloud patterns. You'll be even more successful, and hopefully you'll build some great stuff with it. To learn more, here's a couple great resources. The first two are documents and white papers that we've written that can talk about a lot of these patterns in a lot more depth. The last two then are books out there that you can buy. One from a great MVP of ours named Bill Wilder called Cloud Architecture Patterns Using Microsoft Azure. It's a fairly small book. It's only about 180 pages, but does a really nice job of crystallizing a lot of these patterns and a few more down to there. There's also a good book called Release It, which also talks about it kind of a more abstract level, how you actually deploy and run large sites, and also talks about a lot of these types of patterns as well. And I'll go ahead and post these slides as part of the conference materials. So I'll send the conference organizers them so you can go to the website and download them. I'll also go ahead and be doing a blog post and post the slides and the samples as well, so you can go ahead and check it out. And if you haven't, go to windowsazure.com or go to azure.com, and you can sign up for Azure. Everything I showed here today, you can now go ahead and do yourself. And hopefully you saw some stuff that you liked. It's pretty easy to get started. You can do really powerful stuff, and I look forward to seeing what apps you build with it. So thanks a bunch. And we're out of time, so you're welcome to leave. But if you have questions, I also be more than happy to stay and answer questions.